In this video, I will discuss a JEE Advanced PYQ from the topic waves. This question is based on Doppler effect of sound. Consider a source which is emitting sound waves in all directions. Let there be an observer here. Let the frequency of the sound emitted by the source be Fs, and the frequency of the sound as it reaches its observer, let it be FOB. Now, can you relate these two frequencies? We can expect these two frequencies to be equal if both the source and observer are not moving, they are at rest. But suppose with a velocity VOB, then the observed frequency or the sound frequency when it reaches this one will be slightly more than this source frequency by a factor C plus observer velocity by C. C is the sound velocity in the medium. Sound speed in the medium that is there between these sound source and observer. And if the observer is moving away from the source, then the frequency of the observed sound will be less than the source frequency by a factor C minus VOB by C into Fs. So basically the frequency of the observed sound will increase if the distance between the source and the observer is decreasing. That will happen when the observer is moving towards the source. And when this distance is increasing, the frequency will drop down. That happens when the observer is moving away. Similarly, the source can move. Suppose the source moves with the velocity Vs towards the observer, then the frequency will increase by a factor C minus Vs. Similarly, the source is moving away from the observer, the distance between the source and observer is increasing, so the frequency will drop down by a factor. So that will be C plus Vs. So this is the full formula for Doppler effect, where the observed frequency and the source frequency are different by a factor C plus or minus velocity of the observer divided by C plus or minus velocity of the source. So this plus or minus sign can be decided by the physical reasoning. If the distance between the source and observer is decreasing, then the observed frequency will be more. And if the distance is increasing, the observed frequency will be less. So here there are four possibilities. The source and observer are moving towards each other. Here the frequency will be maximum because of the source movement, frequency will increase, and even because the observer movement, the frequency will increase. So in this case, the observed frequency will be maximum. That will be equal to C plus velocity of observer by C minus velocity of source into the intrinsic frequency of the source. So frequency to be maximum, the numerator has to be more, so there has to be a plus sign here, and this to be maximum, the denominator has to be less, so negative sign is in the denominator. So the next one, if both are moving away from each other, so the observed frequency will be minimum. So numerator will be less, so minus sign in the numerator, and denominator has to be more for the value to decrease into the source frequency. So third possibility is both are moving towards right, both the source and the observer. So source moving towards right means the frequency will increase because of the source movement. So in the denominator, source should contribute to increasing the frequency. So it should be minus. And the observer is moving away from the source. So the frequency will decrease because of the observer movement. So it should be minus. Observer movement is decreasing the frequency because it's moving away from the source. So observer will contribute a negative sign. The last possibility is both are moving towards the left. Here, source is moving away from the observer. So source will contribute to decreasing the frequency. So denominator has to be more. And observer is moving towards the source, so it will contribute to increasing the frequency. So it should be plus. So these are four possibilities: plus minus, minus plus, minus minus, and plus plus. And when both observer and the source are at rest, these two are 0, then the observed frequency and source frequency are same. There is one more basic concept which is called beats. That will happen when we have two sounds where everything is same except frequency is slightly different. So let me call this a source 1. There is one more source of sound, S2, which is emitting sound waves. So this observer here will receive sound from both the sources. To this source 1, let the received frequency be F1, and due to this source 2, let the frequency of the sound be F2. The condition is F1 and F2 are very close to each other, so both are approximately equal. And these two are equal sounds in the sense the amplitude is same. Amplitude of the sound wave is same for both. Sound is represented like this. So this is the first one, amplitude A. The second one also, the amplitude is same A, but the frequency is F2, which is slightly different from F1. So in this case, this observer will hear both the sounds separately. Actually, the observer will hear the combination of these two sounds. These two sounds will superpose to provide a combined sound. So that sound will have a frequency F1 plus F2 by 2, which is approximately F1, which is approximately F2. But it have a amplitude will not be constant. Here the amplitude is constant. Here amplitude will have a frequency. Amplitude frequency will be the difference between the two frequencies F1 and F2. And this frequency is called beat frequency. So with this basic understanding, you can solve this JEE Advanced question. This is the question. You can read it. A stationary source emits sound of frequency F0, 492 Hz. The sound is reflected by a large car approaching the source with a speed of 2 meters per second. The reflected signal is received by the source and superposed with the original. What will be the beat frequency of the resulting signal in Hertz? Given that the speed of sound in air is 330 meters per second and car reflects the sound at the frequency it has received. You can pause and attempt this question. First, draw a schematic diagram to understand the situation. So there is a source here which is emitting sound at frequency F0, and there is a car here which is moving the velocity 2 meters per second approaching the source. So it's towards the source. So the sound goes here, hits this one and gets reflected, and it reaches here. So this sound will go and hit this one, get reflected, and will come here. So this frequency of this sound, when it reaches this car, since the observer is moving, the frequency will be different from this F0. Let it be F1, and the car is reflecting at the same frequency. So this reflected frequency is same F1. There is no change in frequency because of reflection. But this F1 frequency, when it reaches this one, it will be different because the source of sound, which is the reflecting car, it's moving. Frequency will change either because of observer moving or source moving. That is Doppler effect. In the first part of the sound wave travel, that's from the source to the observer. Observer is moving towards, so the frequency will change. Second part, the reflected sound is moving from here to here. Here the source is the reflecting car. So the source is moving, because of the frequency will be different. F2 will be different from F1. And that relation is given by Doppler formula. F1 will be different from the source frequency because of observer moving towards. So it will be C plus observer is velocity of car divided by source velocity, which is stationary. So this is F1 and C is velocity of sound in air. And this F2 is related to F1 again by Doppler formula. F2 equal to F1. For the second part, the reflected wave, source is the reflecting car, observer is the initial stationary source. So here the source is moving and it's moving towards the observer, so it will contribute to increasing the frequency. So it's the denominator, to increase frequency, you have to put the minus sign. Observer is not moving, which is the stationary source. So using this value of F1 there, we'll get F2 as C plus V car by C, C plus velocity of car by C. That C will cancel this C, and this one is here, C minus velocity of car into F naught, the original frequency emitted by the stationary source. So this is C is 330 meter per second. It's given in the question. So this will be 332 by 328 into F naught is 492. This many hertz is the reflected sound frequency as received by the stationary observer. So it's slightly more than 492 by a factor. This is greater than 1. So there will be beats between these two frequencies, and these two frequencies are close to each other because this is slightly different from 1, not too different from 1. So the beat frequency will be the difference between the two frequencies which are superposing. So beat difference will be difference between F1, original F0 and F2. F2 is more, so F2 minus F0. So 332 by F0 is 492. So this minus 1 into 492. That will be 332 minus 220. So it will be 4 by 328 into F0. Simple calculation. This minus 1 into 492. So difference between these two is 4. So this you have to simplify. 4 will go 8, 2, 12, and then 3. 2 will go 2 times, 41 times, and then this 41, 3 is 123. So 6 hertz. So the amplitude will vary with the frequency of 6 hertz. That is the beat frequency. Six is the correct answer. So this is schematic of the situation. Source is emitting sound at a frequency f0, and this sound gets reflected by a car which is moving towards the source at the velocity 2 meter per second. So since the observer is moving the first part, this f1 will be different from f0 by Doppler formula, and this reflected frequency is same as this frequency which is hitting this car that's given in the question, and this frequency f1 will be different from the frequency f2 approaching this stationary source, because for the second part, source is the reflecting car which is moving towards the stationary source. So f1 will be different from f2 again by Doppler formula. So f1 is related to fs. First part, observer is moving towards the source. So c plus velocity of observer, velocity of car, and source is stationary. So 0 into fs, which is f0. So this is f1. And f1 and f2 are related by Doppler formula. F2 is source is moving, which is the reflecting car, so and it's moving towards, so it will contribute to increasing f2 compared to f1. So denominator will have less value. So c minus v car, and observer is the stationary source, which is at rest. So f1, we have to use the previous expression. So from this we get c plus velocity of car by c minus velocity of car at f0. C is velocity of sound in air, which is 330. So 330 plus 2, 332. 330 minus 2, 328 into f0. So there will be beats between this reflected sound f2 and the original sound f0, because only these two sounds or these two frequencies are superposing at the original stationary source location. So two sounds, they will superpose. You won't hear sounds separately. You'll hear a combined sound. So this combined sound, the amplitude will not be constant. It will vary with the frequency. That frequency is the difference between these two superposing frequencies. So this minus f0. So this minus 1 into f0, which is 492. This minus 1 is 4 by 320. Simple calculation. Answer is 6 Hz.